One of humanity's most productive scientific instruments is currently experiencing systemic hardware failure while slowly falling back toward Earth. Yet, despite operating well past its original 15-year design life, the Hubble Space Telescope's 36th year in orbit produced some of its most detailed astrophysics. This split-screen comparison of the Trifid Nebula shows exactly how. By returning to this region in 2026 and comparing it to baseline data collected in 1997, astronomers tracked the measurable expansion of a plasma jet over 3 decades. Capturing this temporal data was possible because NASA engineers implemented a strict software intervention in 2024, shifting the observatory into what is known as one-gyro mode. At the same time, an intense 11-year solar cycle is accelerating atmospheric drag on the spacecraft, creating a high probability risk that Hubble could re-enter the atmosphere as early as 2028. The telescope's continued operation now relies entirely on using algorithmic ingenuity to replace degrading hardware, fighting a continuous two-front war against both orbital mechanics and component decay. Hubble operates without onboard chemical thrusters. To hold a deep space exposure, the telescope must maintain a continuous target lock with an accuracy of 0.007 arcseconds. Inside the pointing control system, 4 reaction wheels steer the spacecraft, guided by fluid-floated gyroscopes. Deep inside are microscopic flex leads carrying power and telemetry through pressurized fluid. Over years, corrosion degrades these leads, creating electrical biases in the rate data. Eventually, the sensor reaches a critical fault state called saturation. The corrupted gyroscope erroneously reports the maximum possible movement rate, forcing the telescope into a protective safe mode and halting all scientific observations. Throughout the mission's history, 33 individual gyroscopes have succumbed to this exact wear mechanism. With hardware redundancy exhausted, engineers had to build a mathematical solution. In 2024, NASA officially transitioned Hubble to a contingency protocol. The logic is direct. Keep the single healthiest gyro active, place the remaining functional unit into a dormant reserve to preserve its lifespan, and delegate the rest of the pointing control to a sensor fusion algorithm. This flowchart maps the protocol. Stage 1 uses magnetometers and the gyro to orient within 10 degrees. Stage 2 engages star trackers to narrow the aim. Finally, fine guidance sensors lock onto guide stars, achieving the 20 milliarcsecond stability required for a sharp exposure. While this process ensures the data remains pristine, it introduces severe operational constraints. Hubble's slewing speed between targets is drastically reduced, and the restricted field of view means it can no longer track fast-moving objects closer than the orbit of Mars. The extra time required to carefully orient the telescope via this software workaround permanently sacrifices roughly 20 to 25% of the observatory's overall scientific productivity. But internal hardware failure is only half the equation. Because Hubble lacks an onboard chemical propulsion system, it cannot independently fight off orbital decay. The Earth's upper atmosphere is highly sensitive to the 11-year solar cycle. During a solar maximum, intense ultraviolet and X-ray radiation from the sun heats the exosphere, causing it to thermally expand outward and subject the telescope to a much denser field of atmospheric drag. The numbers reflect a rapid descent. Deployed at a safe altitude of 612 kilometers in 1990, drag has pulled Hubble down well below 500 kilometers, establishing projections for an uncontrolled atmospheric reentry by 2028. To address this, the commercial space sector proposed a physical intervention. In 2022, NASA and the Polaris program launched an unfunded feasibility study to determine if a commercial crew Dragon spacecraft could safely dock and propulsively reboost the observatory. Executing this maneuver introduces heavy engineering risks. The primary challenge is managing the structural torque limits of the telescope's aging solar arrays and appendages during a sustained engine burn. In the absence of a crewed mission, independent engineering teams have modeled non-intrusive alternatives. One theoretical mission architecture proposes a $10 million swarm of nanosatellites that encircle the telescope's main body and secure themselves using a flexible tension ring. Relying purely on friction rather than mechanical docking, these external satellites would act as a sensory shell. They would transmit redundant attitude rate telemetry back to the ground, completely bypassing Hubble's failed internal gyroscopes. whether through a commercial propulsive burn, external telemetry augmentation, or eventual atmospheric reentry, Hubble's physical survival will set the technological and financial precedent for managing high-value legacy assets in low Earth orbit. This intense effort to maintain Hubble often prompts a direct, necessary question: why allocate resources to a 36-year-old instrument when the James Webb Space Telescope is fully operational? James Webb is a complementary observatory, strictly separated by spectral optimization. Because Hubble orbits in Earth's relatively warm environment, it emits too much thermal radiation to accurately observe the mid-infrared spectrum. This diagram illustrates cosmological redshift. As light from the earliest stars formed just after the Big Bang travels across the expanding universe, its wavelength stretches out of the visible spectrum and shifts deeply into the infrared. Webb operates in the frigid environment of Lagrange point 2, allowing it to capture that deep infrared light from 180 million years after the Big Bang. Hubble, conversely, remains humanity's supreme instrument for capturing the high-energy ultraviolet spectrum. This fleet architecture will soon expand with the Nancy Grace Roman Space Telescope. Named after NASA's first chief of astronomy, widely recognized as the mother of Hubble, this new observatory features an identically sized 2.4-meter primary mirror, but they serve entirely different optical functions. Roman is designed as a wide-angle lens, mapping sweeping distributions of dark matter and identifying tens of thousands of exoplanets. Hubble operates as a high-powered telephoto lens, executing precise, detailed follow-up observations on those newly discovered targets. Modern multi-messenger astronomy strictly requires an ultraviolet specialist. Without Hubble, the fleet is essentially blind to a massive portion of the electromagnetic spectrum. Ultimately, the highest value of a 36-year-old telescope is an unbroken temporal baseline of observation. Early 2026 data releases focused closely on the geometric expansion of the Crab Nebula, a supernova remnant located 6,500 light-years away. By tracking the outward migration of the nebula's filamentary structures against imagery taken 25 years prior, astronomers calculated the exact expansion velocity of the material, driven by synchrotron radiation, at 5.5 million kilometers per hour. Newly launched space observatories, regardless of their mirror size or processing power, simply lack the decades of historical telemetry required to measure this kind of astrophysical evolution on a human timescale. Hubble now operates strictly on algorithmic life support, running against a ticking clock of orbital decay and an unforgiving solar cycle. The Hubble Space Telescope has long since surpassed its original design as a static optical instrument. It operates today as a generational living archive, actively measuring the kinetic expansion of the universe.